Hey Tom, this is Denny Pate with Big Bridge Engineers. I was calling to share with you some information about the FIU pedestrian bridge and some cracking that's been observed on the north end of the span, the pylon end of that span we moved this weekend. So we've taken a look at it, and obviously some repairs or whatever will have to be done, but from a safety perspective, we don't see that there's any issue there, so we're not concerned about it from that perspective, although obviously the cracking is not good and something's going to have to be done to repair that. But at any rate, I wanted to chat with you about that because I would suspect at some point that's going to get to your desk. So any rate, call me back when you can. Thank you. Bye.
It's going to be an update to a previous video I had where I show the cracks in the members. I put the cracks in those members in the wrong location. I put them over here, and I believe I put them in number 11. I should have had them in number 3 and number 10. Now let's go over that again so I can give you a correction and update. As we see, this is the report that no longer exists publicly. It's been removed by FIU. And the report shows that post-tension bars number 2 and 11 stress, okay. So we have, let me just read off, sorry about that guys. A visual inspection of the main span truss members 2 and 11, so they were talking about 2 and 11, were stressed. Cracks were found at moments of the inspection. These have been identified per truss members and consequential numbers within the member. The intent is to monitor these cracks after the bridge is fully tensioned and the main span is at the final location. Now he's talking about 2 and 11, right? 2 and 11. We're going to jump to 10 and 3, though, in his report. Truss members, so they inspected the truss members on 2/6/18. Bars number 2 and number 11 were stressed. Okay, visual inspection of main span truss members. So he came out, visually inspected on 7 days later, after they lasted on the 30th, 7 or 8 days, however you look at it, 31 days in January. Visual inspection of the main truss members on February 6th, after post-tension bars number 2 and 11 were stressed. Now let me just jump right there. He did it after number 2. Hold on, I'm trying to get the thing to jump screen for you. After 2 and 11 were stressed. If you go at the stress, find the superstructure precasting main span and the way it's supposed to have been stressed. Here's number 1. Number 2, after concrete compression is a 6,000 psi stressed post-tension members. Stress post-tension members of the main span in the following sequence. 1, stress deck longitudinal tendons. So he's already out there before you get to 2 and 11. This should already have been done, the entire deck. I'm sorry. Tendons, stress longitudinal tendons, D1 in there. Stress canopy longitudinal tendons, C2 here. C2 is right here. See C2 in the canopy? There's C1, C3, C4. But C2 in this 2017 stamped drawings is offset. But as you know, we saw the post-tension tubes on apparently C1 is now underneath the node, underneath the blister bar. That would make you also think that, heck, all of them are now straight now, in line, and no longer have this profile as this, that they're in line. So C2 is pretty close. If we follow C2's path, I'm going to jump in part of this video again, is the editing software. This would imply that C2, so this implies C2 is very structural because C2 is going to be the strong back for this bridge, while C2 is the first one you see there. There's 2 of them. The other one is C3. So as you look at the profile, so this what is C2 and C3. C2 and C3. But C2 is now straight across, is no longer offset, as I think as we saw in the drawings. I mean in the real world issues. Here's C2 right there. Here's C3. In real life, C2 again goes straight across. And here's the blister bar. Blister bar is coming out here roughly like this. We have 2 other, as I'll show you later in the video or just now. That you'll see 4-inch spacing of the conduit, and then you have the C2. So this makes a huge area of voids. It's just amazing. So we went over that in the other video. Then we move to number 2 and 11, which he's talking about now, which is stress post-tension bars and diagonal members 2 and 11. Okay, after you do these two, there's plenty more down this list. Now watch this, so realize that. So he's out there at this point though, because he says, the members showing these small cracks are truss members that share the same blister at the canopy of the already stressed members number 2, which was done, that was done on January 30th, and number 11, which was done on January 29th, the day before. We believe, so when I say that, so we go back, 2 and 11, that does not count 10, that does not count 3. Now this is crack analysis, so we're trying to figure out where these cracks, how do they produce themselves. So we'll get to that. I only have 7 images to go through. Okay, thus creating cross-sectional cracks, transferring tension loads to the steel on these members. So in a report, it implies that you'll see that it's saying tension created cracks, not compressive forces. If that's the case, why do we have longitudinal cracks, which he's clearly just given us spot shots of it, but this appears to be in line with the rebar that you saw in the NTSB's photographs. A video we show the bar in line with the broken, with the tear out the bottom of the whole of this, of possibly this member here. It's kind of an odd thing. Now the other one more shot at this one for you is, I speak further in the video about how the center span could be coming, deflecting, getting you this action here. Also, we don't know how these joints are down here, how they did it. So we could have something as simple as that. We just don't know. We do have a coding over here that we have to give more respect to, that this engineer, as I said in the previous video, says he's inspected this at the time of this incident. But clearly they applied a coating before his inspection. I find it odd because if you watch the move video, they have so many BPA, the move of the device there. They've got tons of BPA people out there. So I find it odd that they show up 7 days later to do this inspection after this was post-tensioned. It's just, we believe this first stressing, this number 2 and 11, operation has temporarily created tensional members number 3 and 10. So we go to 3 and 10. It'll tell you here, number 10. Here's number 10. Approximately 150 inches measured from the bottom of the member. Okay, and then number 10 again, 168 inches. And then we have, so that's 10. And here's number 10 again. So 10 has the multiple breaks in it. This is multiple breaks here, 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 and here. 4 breaks that he's speaking of, and 2 here. I'm not saying there's not more. He's speaking of 4. All right, and 2 on this one. After they did number 2 and 11. Okay, we believe this first stressing operation has temporarily created tensional members number 3 and 10, thus creating cross-sectional cracks, transferring the tension loads to the steel on these members. No other truss members within span 1 show any cracks similar to those shown on members 3 and 10. So we're talking crack analysis again, remember? So let me bear with me, let me get to that image. So I'm going about it differently. We're going to see if we can make these existing cracks happen. And we actually have a report that can talk to us about that. And then from there we can figure out why Denny Pate and that whole meeting, that group of people, decided that they should post tension again. Okay. So the engineer report says that they did 2 and 11. Multiple cracks showed up. Let's assume now, just for a moment, that they did not continue down this load, down this path. That was the wrong wording. They didn't continue down the process of post-tension and the rest of these. That the inspector was there, and he was there after. He missed both appointments because he's not mentioning that he was there doing any of them. So we're going to go on back to the paperwork. And so that's when we created these cracks here, which tells you that post-tensioning this and post-tensioning 2 and 11 actually puts stress and loads down number 10 and number 3. A significant amount of loads. It doesn't release, or at least release it, does it? Or did it put it under tension, as he said? So he's calling these, what, tension cracks, that you're pulling so tight that you're creating a camber in this bridge, elongating number 10 and 3. Is that his word of tension? Okay, because he says here, we believe this first stressing operation has temporarily created tension in number 3 and 10. Now, tension, again, is referring to a typical truss member, right? Tension pulling on it. As we know, this was going to be under tension anyway, right? Moving back. At least that's what we think. No other truss members within span 1 show any cracks. The intent of the report is to inform the design build team of these cracks. It is the design build responsibility to assess them and determine if these cracks were expected while tensioning and monitoring them. So he's saying these are actually separation cracks, if you will. Cracks that pull away. Here's where I have an issue with that. If it's pulling away, how do you get out 4 cracks? If it's already separated and caused a separation here, how does it still manage to cause a separation here under tension? If it's cracked, you can't bridge a crack with tension still. And I get he's calling it tension cracks because he doesn't see like compressive forces inside. They're like they're crushing cracks, or like bursting little edges. So he's going with, well, what you're going with what you think it might be. And yet it was able to pull, in his theory, for the tension he's thinking of, pull 1, 2, 3, 4, and then pulling on this one 1, 2. Taking note of the shape, this one actually would apparently causes more tension cracks in 10 than 3. Let's go back to this. So we're backing up. Come on, baby. All right. So if we can only see these cracks in more detail, we better go about it more. But he's implying going about it more. He's implying that it's pulling away, tensioning this way and this way, not as in tension as in a member having tension on the underside of one side, and the tension crack shows in the bottom half of it. This is implying that tensioning numbers 2 and 11 created breaks and therefore forces in number 3 and 10. We scroll down now. Oops. And here we are on number 3 now. And here are the cracks again. So he says none other was observed, as he says further down. Well, there shouldn't be any other observed because he shouldn't be over there yet. All right, so as you see, you can see how these things just pop out in number 10. The depth of them. But he didn't want to use his crack monitor on that one. No, that would be not right, would it? All right, so we're gonna take note of that. So putting tension on this created tension. Putting tension on 2 and 11 created tension in 10, creating cracks. Okay, so we go down here. They continue on. They said to monitor. Next, they're going to do post-tension bars and diagonals number 2 and 11, right? Stress deck. So this is not 3 yet. When we come to 3, moving on, stress post-tension bars and diagonals 3 and 10. So this apparently would close those cracks back up, you would think, right? We all know that once you close it up, though, if you close them up using 3 and 10 to close these cracks up, that would have a counterforce against 2 and 11. Which would mean you probably would have a prop because you probably put it up to the kips they were supposed to. So then it probably would pull this back down again. Pulling the deck back down again. So maybe they went back at it again, as we're theorized, to get it back level again. So you go back at 2 and 11 again. We just really need to know how many times they went at adding post-tension notes, how much of it was just a mystery to them and just guesswork. Okay, VSL could report that for sure, I'm thinking. Denny Pate should be able to report it. And surely FIU and BPA. BPA is only going to be able to put what they see, but they apparently had people on there continuously. Let's go from here now. Next paragraph. The members showing these small cracks are truss members that share the same blister as the canopy of the already stressed members 2, stressed on January 30th, and the day before, stressed on January 29th, number 11. This is number 11. Sorry, guys, I got to move this over a little bit so you can see a little better. We believe, that's BPA, who are the inspecting engineers, all of a sudden are now making a conclusive statement. We believe this first stressing operation has temporarily created tension on members number 3 and number 10. So they believe stressing in this one and this one created a stress on number 3 and number 10. Let's go over that again so we can get this 100% clear. We believe that the first stressing operation, which is up here, has temporarily created tension on members 3 and 10, thus creating cross-section cracks. I believe this is what he means by cross-section. Cracks similar to those shown in members 3 and 10. Okay. Transferring the tension loads to the ceiling of these members. No other truss members within the span 1 show any cracks similar to those shown on members 3 and 10. Well, we already talked about that. Similar means it had to be exact. I can say similar. I can find what you and I would think are similar. This crack and these are similar. But I can identify this as nothing else similar compared to this one. It's your evaluation. Okay. So now my evaluation says if I don't see this pattern, then nothing similar to it. That's my out on that. That I'm thinking is an out. With that said, if you see these cracks, this is the, I think it's the, this might have been the, I am not going to say that. Moving on. So now we're going to get the location of those. We go to the next one. We show truss members 3. This is 3. And referring to them as truss members, not a diagonal. Approximately 7 inches measured from the bottom of the member, extending across the cross section. So I don't know if this is the truss member right here, but the bottom of the member here is the bottom member here. You know, where's the bottom of this member? Where it changes direction, so we'll put it there. You call it, or is this still the member because it's got the post-tensioning in it? So it's a measurement from here. So these measurements are variable. So here's 70 inches and 77 respectively, and they're not to scale. So you've got cracks going across. And let's go on from there. So then we move on to the next statement, which he's referring as T10-1 and T10-2. So it appears that these are 210-2. So the truss location, truss member 10. So we're in this member, 10. Approximately 119 measurements from the bottom of the member extending across the cross section. Okay. Maybe I made up the deck part, right? So we got 119, and we're going to have another one at 126, and he's going to mention another one, 150 and 168. So this one's taken on a significant amount. We don't know when they appeared. Did they appear when they compression this one, when they removed the forms or not? But his statement is ambiguous and not, and there's a sizing of it, and of course we know that the inches are different sizing. That was an issue I said in the other one. And same thing here. He's mentioning this inches, and then he's changes it to here. Correct. Type this less than this. Can't be less than that. Okay. Location number 10. We're here again. Approximately 126 inches. Measured from the bottom of the member. So we've got 119 and 126. And there we go. 119 and 126. And we got the 150 and 168 as identified in the next shot. Locational members number 10. My previous video, I put them over here when I put them on number 2 and 11. And that was my confusion, I believe. And here we go. Bolt perts, my responsibility, Red. I actually had somebody else do the graph for me real quick. Bolts perts. Let's move on from there. Let's talk about this crack that NTSB wants us to focus on. And that's the crack there, right? They want us to drive down to that one to take real responsibility on that, to own it. While I'm here, let's go ahead and look at photo 1 and 2. Look at the craftsmanship. And we didn't address this. We didn't address this craftsmanship. Look at this. You know, what do they do? This is just ridiculous. I have no idea, this form work. Look at the raggedy edges and the raggedy edges here and all these cracks and etc. Now, NTSB is now pointing us over to this direction. Take note of the pipe that's on the ground here and here. And they want us to believe that this crack is of issue. And we see we got some more spider cracks, or what I'm referring to, as I just call them. meaning just go off, they tie off, is how I like to refer to spider cracks. From there to there. Now, I will say this, I grind concrete also. This looks like concrete's been ground right there. So, you know, why are you grinding concrete there? I mean, that's ground concrete. You're not getting that finish. That's how you remove, when you're removing, when you grind concrete, if all the paste is being pulled off, you come down to the, yeah, that's what you look like when you're grinding concrete. This is not ground concrete. But this crack here, follow, this is the crack that they keep showing us, but they're not focusing over here. By default, this is movement away from each other, right? So you got tension somehow, creating somehow through center span bowing or whatever. But if you got the center span bowing and you had the top canopy bowing at the same time, this would be a compressive failure, sort of like you would see there, but this is open. So this means it's like a tension failure. The conflict I'm having is the only way to get tension on here apparently would probably be to pull, this is number 11, you'd have to pull down on 10 to change the node's balance, pulling 11 up, if you will. Believe me, it's kind of odd, right? But 10 has no post-tensioning on it at this point. It's got dead weight. The only thing that's an acting force at this time, a real acting force, is that the number 2, C2, has been post-tension. Could the top of the canopy have been made taut and actually flexed upwards and pulled number 11 to create this action? Because remember, this is supposed to have happened after they post-tension, which means made compression in number 11. So how do we, if they make compression number 11, how do we get a gap down there? Yeah, we still have to justify movement somehow. Conflict to that, because I got to have a conflict to that, is if this is tension, how come this is not crushing on the upward movement? How come these are not doing that? And then the other picture too is the alignment is wrong on the other one. But I can't discard, so I'm going to count this as separate, and I cannot discard that this is separate. This appears to be the pipe near the end of 12 and 11 connection, and so that's pretty much all compressive area over there. So how do we get that gap? We've got to pull some tension. We've got to be able to pull this thing back. Could it be just a simple control joint, expansion joint, or something like that, where the two of them come together? Yeah, it could be. I want to see some compressive cracks here, though. I want to see some blowout here, something. I want to see something down here. Now, this is the crack monitor, a pencil line. Just blow me away. I guess this is crack monitor. Blow me away, BPA. Here. Because the inspecting engineer, as I said, is giving soft reports, conflict of interest, in my opinion, negligently, or we don't have more photographs. Remember, we're missing photo 7 also. But now we got this one coming across here. Now I'm going to tie this in for you. And of course, we've got a movement away from this structure, away and down, if you will. Away and down. So here's the tightness here. Here's the opening here. So this implies that to pull that down, you have to have a sag towards the center of the span here, coming here and here, sagging downward, would create this action here. Now his hand's there, which we don't need a hand at this point. I mean, clearly it's a photograph. You know, I'd like to see this crack, which we're seeing here. I'd like to see more of it as it migrates across this direction. This is what my thinking is, that they were doing the repairs on this deck, this VSL company, as per Denny Pate's demand and FIU and everybody else in the meeting. With that said, if you were to try to close this crack up, this is the one that NTSB kind of is making us look at, smoke and mirrors crap, wanting us to look at that, the silliness over here. This crack here, limitedly so. I don't even think they... Here you guys go. Apparently, number 11, when they detensioned it, cracks showed up. But we don't know where these cracks showed up at. If they showed up at the base where the arrow's pointing now, and I'm doing a voiceover here, the problem I have with that is that column is supposed to be under compression. How do cracks show up when it's got compression on it? It's already closing it down. Now, the only other way is if there are cracks that you would want to close up. If you detention number 11 and cracks showed up, they would have to be at the underside of number 11. and you'd panic and want to close those up. But detensioning number 11 on its own, since it's under compression, you would get buckling, etc. But you wouldn't get cracks opening up. Now at the slide at the bottom there, could that slide? Well, we know number 12 is stationary per the evidence that's left behind. So let's go back to the original problem of number 10 opening up. So they detension 10, number 11, and all of a sudden these cracks show up, or they show up larger. Remember, there were cracks in it before, and we don't know if they fixed them or not, but that sort of doesn't matter at this point because they detention. Cracks showed up, which would indicate or imply that the bridge was sagging. And then they try to use number 2 and 11 to pull the bridge back into position, not just to get rid of cracks, but to level the bridge again, literally level the bridge again. So they use 2 and 11. 2 played along because 2 is a different diameter, 3-foot member and different location of the post-tension bars, etc. Number 11 did not play along, as we can see that it already had a significant amount of damage to it. So 11 along with 10 didn't want to play along with this extra, this reversing forces, if you will. That's my guess on that. So when they started post-tensioning again, they just kept forcing it, trying to make it happen. And maybe the post-tension bar did break at that point. But nevertheless, the bottom of 11 has open cracks, which again are not compressive cracks. Those are tension cracks. So it appears that number 10 might switched off and decided it was more compressive than number 11 based on the ability to change its, and as I said a long time ago, might be to change its forces on these nodes by adding extra compressive forces in which would be done with tensioning with the post-tension bars. Man, this thing was just a wild playground. It was a wild playground. But again, if you see openings at the bottom of 11 in the photographs, remember we are looking back in February, though. We're not looking at the images of the incident that happened that day that it collapsed. So we don't know what the cracks look like. So with that said, I am making my statements on the craziness of this design based in February and trying to predict the collapse in March that we have not a single image of besides a video. That the images I'm showing you right now on the screen means nothing. That is 2,000, well, it means nothing unless NTSB shows the image and go, oh yeah, this is the crack. But no, cracks don't get smaller, they get bigger. So if they decide to close this bridge back up, those cracks got larger. If they decided to retension real quickly, or should I say real in a panic if you ask me, if you make all your evaluation in 2 hours. Look, I've been playing it with this, with you guys for 3 months, and it's not, and I've only got this little bit of data. But they had all the data, and they made a snap decision within 2 hours, and they've got BPA telling them what they think the reverse forces are, and possibly rebar, and it's just craziness. Bottom of the deck. Well, it would clearly close up this crack, but wow, how much movement was down there? It didn't look like much. The indicating movement was at the top of this one, which, let me grab the image again, was at the top here. As this is more open, and this is closed at the bottom. So if you had a sag in the middle of the deck, that does it. So this is the original NTSB photograph that they released. And so I believe that post-tensioning, this is the crack you see mimicking on the outside, is when they post-tension this, it's created a buckling effect in this rod here, which bowed out and cracked it. Now it's also bowing, it might have came in contact. This is that number 10, and so I'll explore that a little bit. This is the number 3 and number 10 cracks might have also, what is bowing out, put these under tension is what he might be referring to on the backside, and forced them to exhibit their cracks in the columns at odd locations, not just everywhere. So it's showing you where the forces are. So I think that's in line with that post-tensioning, the reinforcement, the rebar. So the cracks, as these exhibit themselves, they're actually showing you where the load forces are exhibiting themselves on the literal structure. So if you're post-tensioning these, what he alluded to, that the post-tensioning of these 2 and 11, these created these cracks, is what he's alluding to. Notice what the report says, that post-tensioning these cause these to exhibit. And we got detensioning. Cracks apparently have showed up again. And we know that because Denny Pate's comment and the 2-hour meeting. And then they went back up there to do work. At that point, VSL is now crack addressing as far as I'm concerned. And that's the only one I think we're just being sent down as silly smoke and mirror place. Now, how much bending do you need to create a little bit of a crack up here that we saw? I'm sure there are other photographs they're not releasing. We should be looking at the crack of the day of the accident, the 2-hour meeting. But NTSB is withholding that information from us. Now, let me jump to one thing here. These are 1 3/4 inch rods, right? As we recall, you guys can take the pick. 1 3/4 inch rods. All 1 3/4 inch diameter post-tension bars will have an 8x12 anchor plate. These are the 1 3/4 inch rods, as we know per the plans. Okay, for post-tension bars, stressing and grouting. Number 2, let's go to number 11. That's the one we have the clamps on. Bar size, 1 3/4 inch, right here. So we have the 1 3/4 inch diameter bars, as we right here. All 1 3/4. Look at my mouse here, please. Diameter post-tension bars will have an 8x12 anchor plate. That means here, 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 and here. That's a huge plate. Let me scale that roughly. Do a terrible scaling for you. Let's slide over. This is GG. This right here. Pulling over to the drawings to show you guys, it's GG, GG. And shows, let me enlarge, that it will be 2 feet by 1 feet 9 inches in shape. That this will be 10.5 inches, 10.5 inches. So these will be center line, these post-tension bars. The scale will be such that it will be 4.5 inches from the outside edge to center line, and this to center line. So as we look at this, let's see if I can do this properly. This is that's the 4.5 inches. 4.5 inches. As we come over here, that's the 4.5 inches. So we're looking at the wider part, the 2-foot part here. Let's slide this over a little bit, not much. So this is 2 foot from here to here. And the underside is the 1.9, is 1 foot 9. Now then we have plates that go on this that are going to be 8x12 plates. All 1 3/4 inch diameter post-tension bars will have 8x12 anchor plates. 8x12, 8x12. 8x12, 8x12, because these are 1 3/4 inch bars. We slide over here. I did a rough scale, 12 inches, right? So that gives me 9 inches left. This is only 1 foot 9. Now, if we turn them the other way, the plates would be sticking out the outside end. So they had to have it configured in this manner. So that's the manner as you imagine it going up to the top of the node. You can't turn it the other way. They just don't work. That'd be 24 inches, and we'd be seeing plates on outside of well, we wouldn't see plates. We're now going to carry on to, let me show you where. So now we look at the blister bars. If this is the width of it, so that's 1 foot 9. Center line off the width, we talked about this, so they're going 1 foot 2 inch off. So we're 8 inches away from 2 2-inch conduits. So this is center line. This is halves, as I always made a mistake in my previous video, confusing you guys. So center half is 9.5 inches from the center of that column to where you start having an opening, this void. So the post-tensioning rods will come diagonal down this column right here. This is a half. Would have been within striking range of the outside of this void. 4 inches before you then made it over to a void that's approximately, well, that's the outside detail. But right here might be the duct. So let's call it 3 inches. And then we got Denny Pate. As a lead technical designer, FIG Engineers Denny Pate, PE, will benefit the project with his extensive experience in design of over 30 complex. Yeah, well, this one was too much for him then. Signature cable-supported bridges. Well, this is not a cable-supported bridge, isn't it? Therein lies the problem. You tell me you're bragging about 30 complex signature-supported cable-stay bridges? Well, this wasn't one. You would see if I added that layer. That's the crack right about there. You see it's in line with the post-tensioning. reinforcement. So I don't have an issue with it, as I told you. I don't really... You got it way too scaled up. Oops. Yes. So we got number 12. Number 11, we got a crack. So when I do that, and I come here to this little guy here, come on. I lighten that guy up. You now can see where the crack is on the bottom of the deck. It's about 8 inches, and I think it's on the outside of the column. So this helps you guys visualize it. I visualize it like this for you guys when I see it. So over 40% of the team at MCM are FIU graduates, creating great pride in the opportunity to create an outstanding bridge for FIU and community. Apparently that's not so, huh? But this is what we were talking about, or most of us are talking about, is that they're tied in FIU. They can't trash them without trashing FIU. As the construction project manager, MCM's Rodrigo Izaya will provide project construction leadership and oversight. This person's negligent. They didn't do a good enough job, in my opinion. Now, this is what they were going to do, providing dedicated pedestrian routes shielded from construction work areas. Well, this was not shielded from the pedestrians. Once main span is erected, additional work to complete the main span construction will be performed over off-peak lane closures. February 28th, there's my letter. Photo 7, where are you?